This video is going to be about reading a position versus time graph. And the learning target is I can use a position versus time graph to calculate the velocity of a moving object. So let's say we have this iguana here and he's getting a little hungry. He sees some food over on the other side of, a big open area, and he's going to start moving towards there to go get some food. And he's actually pretty quick. We're going to take a look at his movement and how fast he can move and where he's at. So we're going to put a stopwatch on him and we're going to measure how far he gets every second as he makes his way over to go get some dinner. And so in the first second, he travels at 1 second and he makes it 10 meters. Let's say in the second second, he makes it 220 meters. In the third second, he makes it to 30 meters. In the fourth second, he makes it to 40 meters. And by the fifth second, he's made it almost all the way to the food, and he is at 50 meters. So we can see how his movement changed over time and how far he was making it each second. And so to give us another representation of this, we are going to make a graph of this data. So we can see that we have a graph of his movement on this graph right here. The only thing that we need to add to this is a title. We've got our independent variable right here of time, our seconds that we measured here, and we've got our dependent variable of our position, and we also have the units of both of those. So we're just going to add a title to this, and we're going to call it a position versus time graph. Some places that you might see this could also be a displacement versus time graph, and displacement is really the overall distance, the net distance that he has traveled. If he was moving backwards, then his displacement would show that he was moving backwards, even though he was still moving per se. So like if he started off here, moved a little bit, and then went backwards, we would be measuring to his position at that time. If he was at 1 second there, let's say he went out for a half a second, then came back, his position would be back here, even though his distance would really be this distance plus this distance, and that's displacement, remember. So if we were going to try to find out more about his motion based off of this information, if we're trying to calculate his velocity, we can see that in this little section right here, his velocity is distance over time, and his velocity equals 10 meters divided by 1 second, and his velocity is 10 meters per second. And in this section right here, we can see that he traveled another 10 meters in 1 more second. And so his velocity was again 10 meters per second. And we can see the same thing going in each of these 1 second intervals. Each 1 second he travels 10 meters. So we know that if we calculated his average velocity, remember average velocity is the total distance divided by time. We could say that the velocity was 50 meters divided by 5 seconds. And his average velocity would be 10 meters per second. I can also see the same trend on my graph. So if I look at how far he's traveling and how long it's taking him to get there, I can go, he traveled 1 second and he made it 10 meters in this first increment. Now, after 1 more second, as I'm moving across my x-axis, going from 1 to 2, he moved another 10 meters. My position is increasing by 10. And this is going to continue all the way across here. As I go 1 second, 10 more meters. 1 more second, 10 more meters. 1 more second, 10 more meters. And I can do the same thing across my entire graph. So now if I took, so actually I can say each increment, he moved 10 meters in 1 second. And so he had a velocity in each of these intervals of 10 meters per second. And I can do the same thing with his entire movement. Right, so if I go the entire time, 5 seconds, he moved 50 meters. So my velocity, my average velocity is 50 meters in 5 seconds. My velocity equals 10 meters per second. And so you're probably seeing a trend here. And we can tell that velocity, we know that velocity, has a equation of distance divided by time. In a position versus time graph, our distance is on our y-axis and our time is on our x-axis. And so if you remember from math class, the slope of a line equals rise over run. And our slope of a line, the equation for this, is y2 minus y1, the change in our y, divided by x2 minus x1, the change in our x. And so if we look at this from our graph point, we can see that for this first interval, I'll go red, the change in our x was 1 second, and the change in our y was 10 meters. So our slope is therefore, running out of room here, slope equals 10 meters divided by 1 second, which makes our velocity 10 meters per second. And so the important part of this is when you're reading a position versus time graph, the slope of the line is the velocity of the moving object, because it's the change in the position divided by the change in the time. And so let's take a little bit of time, go back and try this on your own. Try to answer these 4 questions using the information we just went through. What is the average velocity from 2 to 6 seconds? Is it traveling at a constant speed during this? What's the object's velocity at these other 2 times, from 6 to 8 and from 8 to 9? So for this one, if I'm looking for the slope, remember I'm looking for y2 minus y1 over x2 minus x1. I can outline this from 2 to 6 seconds. My change in my x was from 6 seconds minus 2 seconds. And my y is going to change from 7 right here, or from 0 to 7. So my y2 is my 7 minus 0. And so I end up with a velocity of 7 divided by 4, which equals 1.75. And the units for that are going to be meters per second for that one, because remember my slope equals the velocity as long as it's a position versus time graph. So let's look at that second question now. Is it moving at a constant speed throughout this whole time? Now if we look at this, it can be a little bit hard to tell. If we look at right here, see what happens there? There's a little bit of a kink. We're going with the slope of right about here, and then all of a sudden our slope changes in the second part to a little bit of a steeper slope. So I'm trying to outline that. As you can see, this is a steeper slope, and because the slope of the line changed, we are not moving at a constant velocity. The velocity changed right at that point where I circled at about 3 seconds. So on this one, what is the object's velocity from 6 to 8 seconds? Remember, slope equals the velocity as long as it's a position versus time graph. Slope is y2 minus y1 over x2 minus x1. And so our velocity, I'm going to substitute that in for slope. Our velocity is, our y2, we're going from 6 to 8 seconds, from 6 to 8. So our x, and I always do the x first for whatever reason, 8 minus 6, which is 2. Our y changed from 7 to 7. 7 minus 7, there was no change there. So our velocity equals 0 divided by 2, and that means we have a 0 meters per second velocity. And we can tell that that's true because our slope right here is a flat line. So whenever you see a flat line of a position versus time graph, that means that object is not moving. It didn't go anywhere. And our last one here is, what is the object's velocity from 8 to 9 seconds? We're going to set our problem up in the same way that we did before. Slope, which equals the velocity, is y2 minus y1 divided by x2 minus x1. So our velocity equals the change from 8 to 9. I'm going to go 9 minus 8 for our x. And we went from, let's see, we went from 7 down to 2. And so remember, my y2 is what I ended up at. We're looking at the final y first. So I have 2 minus 7. And so I end up with negative 5 divided by 1. And this is meters. This is seconds. We should have that in here. My bad. And so we have a velocity of -5 meters per second. And we can check ourselves here. We should have a negative velocity because our slope is negative. The position is decreasing. And so since it's a negative slope, we know that we should have a negative velocity. So hopefully you feel a little bit more comfortable reading a position versus time graph and using it to calculate the velocity. The big thing that you need to remember from this is that in a position versus time graph, the slope of the line equals the velocity because it's a change in the distance divided by the change in the time, which is the same equation for velocity.